Hi! If you watched my previous videos, if not, definitely watch them after this video, links are somewhere above me, you might have noticed that I am complaining about microorganisms being transparent quite often. This is mainly because we cannot observe them in high contrast without dyeing them beforehand. And honestly, dyeing doesn't even always work. Dyeing. Okay, this sounds weird. Let's put it straight, using coloring to make microbes more visible. However, I heard about some techniques used to fight the low contrast images of transparent microbes. I was able to borrow this really fancy microscope from my grandpa with which we can test those techniques. Thanks a lot, Grandpa! In order to test them, I prepared several samples. I tested all these methods with a sample of tardigrades which got their dedicated video last time, some pond water with algae and also some other stuff that I found laying around. Let's firstly look at them in a bright field, which is the traditional way of observing stuff under the microscope. We are now looking at ciliates, which have a big amount of tiny hair called cilia, and flagellates, which have a flagella at the end of its body they use to move around. These guys are from a hay infusion, which is a mixture of hay and water that has been sitting in a jar for a few days. If we look really closely, we can see the flagella of those flagellates. However, the contrast is really low because the whole microorganism is transparent. This is what we'll try to improve. Tardigrades, on the other hand, are not completely transparent. This is why we can see them quite clearly even under a bright field. Let's try changing the objective. Wait, is that a brain? It definitely looks a bit like a brain. That's actually really cool. As we have seen, we can observe some microbes in pretty high detail under a bright field. But not the ones which are almost completely transparent. Let's look at the first secret trick we can use to observe the details of transparent microorganisms. The main idea behind it is to diverge all the light that doesn't pass through the microorganism, leaving only the light going through it and a dark background. This is also why this type of microscopy is called dark field microscopy. But you may ask, how can we know which light passes through the microorganism and which doesn't? Well, we don't. We just block almost all light, leaving only a thin ring which is then bent by the condenser into a cone-like shape that passes through the sample but doesn't go to the objective. The condenser is the part that focuses the light from a bulb onto a slide. However, when there is something like a microorganism or a piece of plant in the sample, it bends the light which is passing through it towards the objective. And now we can enjoy a nice, high-contrast image. Let's look at our tardigrade friend. Right now his body has an almost opaque white color, and he seems to enjoy the dark field too. It did not add that much of a detail here, in my opinion, but some features of its body are more prominent. You know what? Let's relax and enjoy the cuteness of this microscopic water bag for a moment. Moving on. We are now looking at pond water. There are some very interesting microorganisms that look like moving sticks. I wonder if the ever-popular stickman got inspired by them. It does not look like a stickman per se, but it could have been a seed of inspiration for the guy who created the first stickman. Jokes aside, these microorganisms are actually called diatoms, and they are really interesting because most of them generate energy using photosynthesis, not by eating other microorganisms. Dark field microscopy is really cool and it beats the transparency of microorganisms, which is what we were trying to achieve. However, some people thought that it wasn't good enough. I honestly don't see any problem with it. It gives me a high contrast image and the dark background is a nice bonus for me as a dark mode lover. Dark mode forever! But those guys didn't like the approach of just hoping that the light passing through an object bends enough to go through the objective. So they started to think about a better solution, and after a lot of experimenting they found one, and it was revolutionary. So revolutionary that in fact the guy who invented this new method called phase contrast microscopy got the Nobel Prize for Physics in 1953. That's cool, but how does it work? In order to understand phase contrast microscopy, we need to firstly stop thinking about light as a ray and to accept that it is actually a wave with a wavelength which gives light its color and a phase. An interesting fact is that when light passes through some materials, for example a microbe, its face changes. Okay, wait. This means that we can distinguish between light coming through a microbe and the background light, right? Yes, but we are not done. This is because humans can only distinguish the color and the brightness of the light, not its face. However, when two light waves meet, they interfere, and the resulting brightness will change depending on the difference between the phases of the light waves. Phase contrast microscopy uses this phenomenon to boost the contrast between the specimen and the background. We can block most of the light and only leave a thin ring coming through the condenser. However, now the background light enters the objective, unlike in dark field microscopy. The light, which passes through a specimen, is scattered and its phase changes too. Now, we put something called a phase ring, which changes the phase of the background light to match the phase of the scattered light. What happens now is that the background and scattered light interfere constructively, which increases the brightness of the scattered light and creates a high contrast image. We can also add filters that make the contrast even bigger. Phew, okay, I think that is enough explaining for one day. Let's look at the microbes. Well, this definitely looks different from bright and dark field. The colors are a little bit weird and... oh, never mind, here's another microbe. The ciliate is bigger than the ones we've seen before. And he's turning around. I wonder why microbes always do that. After some time, he settled down and I decided to look at him with a higher magnification. Okay, wow, can you see the cilia? This is awesome! Phase contrast rules! And remember those flagellates? Now we can see their flagella really clearly. Now I understand why this got a Nobel Prize. By the way, I never mentioned all the bacteria in the background, but we can see them in great detail. They are like everywhere. Let's look at the pond water. If you didn't see any resemblance with sticks before, now the diatoms definitely look like them. There are actually more types of these stick-like moving diatoms. The first one is short and has two dark sticks inside its body. There are also longer diatoms that resemble sticks completely. In contrast to previously shown specimens, this diatom does not really move. And his structure also looks really different from the previous ones. Forget everything about sticks. For these organisms, rectangles are the cool shape. Moving on to our tardigrade friend. He looks a bit weird. But he doesn't mind the weird appearance and just walks and chills around. I think that we can see his brain thing more clearly, but I'm not really sure. Well, phase contrast is extremely cool, but it doesn't look good everywhere. And this is the main message I'd like to conclude this video with. Every technique is good for different purposes, and you have to choose the right one for your needs. But it was really nice to finally see all those transparent bacteria and other microorganisms. So, if you liked this video, like, share, subscribe, and see you later! On to the bloopers! Hi! If you watched my previous videos, if not, definitely watch them after this video. Okay, I'm not off to a good start. It does not look like a stickman per se, but it could have been a scene of it. God damn it! With a wavelength, which gives light its color and a face. God damn it! This is because